In this video, we will look at the language of hypothesis testing. A statistical hypothesis is a conjecture about a population parameter. This conjecture may or may not be true. A conjecture is essentially an educated guess. For example, the population mean is equal to 12.5 inches. A hypothesis test is a procedure based on sample evidence and probability used to test statements regarding a characteristic of one or more population. The characteristics we're talking about, we're going to be looking at proportion and mean. We will perform hypothesis tests on proportions and means for both one population and two. Two populations will come in Chapter 11. Just like with confidence intervals, the formulas vary, but there's a standard 5-step process, and that's what we're going to look at in this video. Step 1 is to state your hypotheses. There are two different types of hypotheses. We have our null hypothesis and our alternative hypothesis. The null hypothesis is symbolized HO and is a statistical hypothesis that states that there is no difference, no change, or no effect between a parameter and a specific value, or that there's no difference between two parameters and is assumed to be true until evidence indicates otherwise. The null hypothesis has a single parameter value, such as p equals 1/3. The hypothesis p equals 1/3 means that the population proportion is equal to 1/3 for a particular solution or a particular situation. Please note that we will always use an equal sign in our null hypothesis. The alternative hypothesis, symbolized H1, is a statistical hypothesis that states the existence of some difference between a parameter and a specific value. It is what we are trying to find evidence to support. Oftentimes, our alternative hypothesis is called our claim. An alternative hypothesis has a range of values that are alternatives to the one that's in our null hypothesis. So remember that our null hypothesis is going to have a statement such as p equals 1/3. So our alternative could be p does not equal 1/3, p is less than 1/3, or p is greater than 1/3. Putting your null and alternative together, there are 3 cases of hypotheses. Our 3 cases are illustrated here. The first, mu is equal to mu naught. Our alternative, mu does not equal mu naught. Our second, mu equals mu naught. Our alternative, mu is less than mu naught. And our third, mu equals mu naught. And our alternative, mu is greater than mu naught. So these are interchangeable with mu or p, mu for mean and p for proportion. This first case is our two-tailed. The next case is a left-tailed test. And the third is a right-tailed test. The value mu naught or p naught is called our null value, and it's going to be some number specified in the problem. Again, case A is called our two-tailed hypothesis test, and that's when our alternative is stating or including values in either direction from a specified standard. An example of a claim for a two-tailed test would be that men and women have different verbal abilities. We're not saying that men or women have a greater or less verbal ability, they're just different. Case B is our left-tailed test because it's claiming that our parameter is less than the null value. For example, one doctor claims that less than 20% of patients suffer from side effects. Case C is our right-tailed test because it's claiming that the parameter is greater than the null value. For example, the proportion of the population that favors the legislator's plan is more than 0.5. Write the appropriate hypotheses for the following situations. Use mu for mean, p for proportion, and sigma for standard deviation. State whether the test is left, right, or two-tailed. A researcher thinks that if expectant mothers use a vitamin pill, the birth weight of babies will increase. The average birth weight of the population is 8.6 pounds. The first thing we want to identify is what is the parameter that we're testing. The word average indicates that we're going to be testing about the mean. So our null and alternative hypotheses will both be statements about mu. The birth weight of the population is 8.6, so this is our null value. And that's what our null hypothesis will say, is that mu is equal to 8.6. The claim is that the birth weight of babies will increase, so our alternative is going to be mu is greater than 8.6. Because the alternative hypothesis has our parameter greater than a specified value, that makes this a right-tailed test. A teacher thinks that the proportion of students bringing their lunch has decreased over the last 5 years. 5 years ago, 50% of students brought their lunch. First, identifying the parameter of interest is going to be proportion, so P, which indicates that both of our hypotheses will be statements about P. Five years ago, 50% of students brought their lunch. That 50% is going to be our null value. But since our statement is about proportion, we have to convert that to a decimal. So P equals 0.5. And then the claim is that the proportion has decreased. So our alternative is P is less than 0.5. Because our alternative is stating that the parameter is less than a specified value, that makes this a left-tailed test. A psychologist feels that playing soft music during a test will change the results of the test. The psychologist is not sure whether the grades will be higher or lower. In the past, the mean was 73. It references mean, which means our hypotheses, and our hypothesis test is going to be about mu. So both of our hypotheses will be statements about mu. Our null value is 73. So mu equals 73 is our null hypothesis. And the claim is that the test grades will change. And it also further says that the psychologist is not sure whether the grades will be higher or lower. So in this case, we're just going to say that we think that the mean is not 73. Because we're including values on either side of the parameter, both values less than 73 or greater than 73, this is a two-tailed test. It has been hypothesized that the standard deviation of the germination time of radish seeds is greater than 2 days. A researcher wishes to test this hypothesis. We're testing a claim on standard deviation, so our null and alternatives will be statements about sigma. Now, the difference in this problem versus the first three that we did was that all they're giving is the claim. They didn't actually tell us that null value by saying it's known that the standard deviation is 2 days. But in saying that we believe it's greater than 2 days, that implies that the null value is at 2 days. So our null hypothesis, sigma equals 2. And the claim is that the germination time is greater than 2 days. So our alternative is sigma is greater than 2. And one other note on this last example, D, we won't be actually performing hypothesis tests for sigma or for standard deviation. But there might be problems on MyStatLab that require you just to set up the hypotheses for standard deviation like we've done here. But you won't have to do any other steps when it comes to standard deviation. The second step in our hypothesis test is to determine our level of significance alpha. Now, we've already talked about alpha. We talked about alpha in chapter 9 when we were learning about confidence intervals. And in chapter 9, alpha represented the area, the total area in both of our tails. It's not actually any different here. Alpha is still the area in the tail, but in the confidence interval case, we always had two tails. With a hypothesis test, we could just have the area in one tail, which we'll look at below. So the first case is our two-tailed test. And again, we know that it's two-tailed because of that inequality that's in our alternative hypothesis. Because it's two-tailed, that means that the area in both tails total is alpha, or the area in each tail is alpha over 2. A left-tailed test has a less than inequality in our alternative hypothesis. And now we're just looking at the tail on the left, and the area on that left tail is alpha. It's not divided because we only have one tail. And then lastly, we have our right-tailed test, denoted by the alternative being a statement that the parameter is greater than a specified value. And in this case, the area in our right tail is equal to alpha. One more comment. Alpha will always be stated in the problem. If for some reason it's not, you'll use alpha equals 0.05. The third step is to calculate our test statistic. We're going to have different formulas for the test statistic depending on the parameter. So we'll learn more about those formulas in our next few sections. Step 4 in our hypothesis test is when we find our critical value and we make a decision. This is probably the lengthiest step and really kind of the bulk of the entire process. Again, considering our three cases, the first case is our two-tailed test. The area in our two tails is alpha over 2. And the values that separate the critical region from the non-critical region, we have a positive critical value and a negative critical value. If it's a left-tailed test, there's only one critical value. And it's going to be negative. It should be blue. If we have a right-tailed test, similarly, we only have one critical value that separates the non-rejection region from the rejection region, and that's going to be positive. Now let's define these terms a little bit more. Again, that critical value is the number that separates the critical region from the non-critical region. The critical region, which is more often referred to as our rejection region, is the range of values that indicates that there's a significant difference and that our null hypothesis should be rejected. So if we're looking at our graphs, our rejection region are those tails. So we have two tails in a two-tailed test. So we've got two areas that make up the rejection region. In a left-tailed test, just the left tail is our rejection region. And in a right-tailed test, just the right tail is our rejection region. which means that everything else is the non-rejection region or the non-critical region. Now we make a decision based on where our test statistic lies, whether it's in the rejection region or out of the rejection region. If your test statistic lies in the rejection region, we reject the null hypothesis. If the test statistic falls outside of the rejection region, then we fail to reject the null hypothesis. Now, just a reminder, we haven't actually learned how to calculate a test statistic yet. We're going to see those formulas in our next section. The top statement on this next page is just what we wrote on that previous slide. And then these extra graphs are just going to reiterate what we saw on that previous slide, highlighting that the tails represent our rejection regions. Typically, we want to reject the null hypothesis. So the null hypothesis is something that we've known to be true maybe in the past, but then our alternative is the claim that we believe. Okay, so how do we think that the parameter is actually different than that null value? Therefore, we have two decisions. As we stated before, we can either reject the null hypothesis or fail to reject the null hypothesis. Because because our decision is based on sample data, our decision could be right or wrong. And we don't ever know whether or not it's right or wrong. So just like with confidence intervals, we never said for sure that the parameter lies between these numbers. We made a statement about how confident we were about whether or not the parameter fell within those values. So again, if we were able to collect data for our entire population, then we would have no need for any of these processes at all, because we would know what the true population parameter was equal to. As mentioned before, we have error associated with using a sample. The two types of error we're going to look at are type 1 error and type 2 error. Type 1 error occurs if one rejects the null hypothesis when it is true. Type 2 error occurs if one fails to reject the null hypothesis when it is false. So in both of these definitions, we're talking about just the null hypothesis. A quick comment, when you're looking at the homework in MyStatLab, a lot of times the wording is a little tricky. You have to be very careful. It'll talk about rejecting the null, and then it'll make a statement about the truth of the alternative hypothesis. So just make sure you're reading critically. How likely is type 1 or type 2 error? The level of significance, which is alpha, is the probability of committing a type 1 error. So in past chapters, we've emphasized that we want alpha to be very small, and this again supports that. We want the probability of rejecting the null when it's true to be very small. The probability of a type 2 error is beta, which is not easy to compute. We will not be computing it. But it is important to note that as alpha goes up, beta goes down, and vice versa. The fifth step in our hypothesis test is a statement of conclusion. We're going to make a statement that says there is or there is not sufficient evidence to support. We're just going to support the claim, and then you're going to give your alternative. So this is the most common way. This is the way that we'll be writing our conclusions, is in H1. So if our decision was to reject, we'll say there is enough evidence to support the claim, and then you'll give the claim that's in H1. If our decision was failed to reject the null, then there is not enough evidence to support the claim, and you'll state your claim H1. Assume we have the following hypotheses. Our null hypothesis is that the proportion equals 0.02, and the alternative, the proportion is greater than 0.02. So that's our claim. What would be our conclusion if we rejected the null hypothesis? Again, I'm going to rewrite those null and alternative. Our null was that P equals 0.02. Our alternative is P is greater than 0.02. If we reject the null, our conclusion would read, there is enough evidence or there is sufficient evidence that P is greater than 0.02. If we fail to reject the null, then there is not enough evidence. That the proportion is greater than 0.02. Once you start actually seeing examples with context, you won't write P greater than 0.02. So you won't write your claim symbolically. You'll write it out in words based on the context of the problem. And just to summarize, the 5 steps for our hypothesis test. Step 1, state the hypotheses, your null and alternative. Step 2, determine alpha, which is most likely given, but again, if it's not, you'll use 0.05. Compute your test statistic, which we'll learn those formulas in the next sections. Find your critical value from the appropriate table. Draw a picture with your critical value, shade your rejection region, and then place the value of your test statistic on the graph, which supports the decision that you'll make. Whether your decision is to reject the null, if your test statistic is inside of your rejection region, or you fail to reject the null if the test statistic is outside of the rejection region. And then you will state your conclusion. There is or there is not enough evidence to support. We will just be supporting the claim, and then you'll state your claim, which is H1. In section 2 and section 3, we'll break down that process even further for just proportions and means respectively.